human studies. So cannabis in the brain, we're going to cover a little bit more in depth in this lecture. The last lecture covered the effects of cannabis on gray matter and white matter morphology. This lecture will talk about the functional effects of cannabis in the brain, and we know about that both from animal and human studies. So let's just sort of summarize what's happening in terms of the functional effects of cannabis use in the brain. So when we look at both reviews of animal and human studies, and there's some nice citations here if you want to look at some of these reviews, those reviews suggest that cannabis leads to alterations in dopamine reward circuits, that cannabis use leads to reductions in CB1 receptors, and it changes stress circuits, and it changes a growth of dendrites in the brain. So let's talk about this more specifically now. If we review human functional MRI studies, they suggest that there are changes in dopamine reward circuits that may be associated with cannabis, like long-term frequent cannabis use, and also changes in emotion regulation. Now, that's not entirely surprising. Obviously, a lot of people report that cannabis changes or has some impact on mood and emotions. However, it's important to note some of the limitations of the literature and some of the inconsistency in findings and potential for type 1 errors. So the animal and human literature oftentimes is contradictory with respect to the effects of cannabis in the brain. In animal studies, this may be related to differences in dose in the drug used, because remember, THC is not self-administered by animals, so they may be using a CB1 receptor agonist and analog to THC. Route of administration can be different across studies. That can cause trouble, and also there are pretty big sex differences, and all of these things can vary study to study. In humans, inconsistencies in findings are likely related to inflated type 1 error. What that means, type 1 error means you find a difference when a difference really does not exist. And that can be due to the sheer number of statistical tests that are conducted in neuroimaging studies in humans. It can also be inconsistencies can be due to differences in study parameters from one study to the next in humans also. Finally, small sample size can be a big problem. In general, small sample sizes can lead to spurious or inaccurate findings, and there are lots of small neuroimaging studies out there in humans, only a few large studies. Animal studies also have small groups typically, but remember in animal studies there's much greater control over study conditions, which increases internal validity. So here's an example of how this works in animals. As I mentioned, animals will not self-administer THC, which can be a problem. And so it makes traditional studies of the addictive potential of cannabis to be more difficult in animals, more difficult than other drugs of abuse, for example. Animal studies, therefore, sometimes use other drugs besides THC that activate CB1 receptors. Also, route of administration can be different in different animal studies. Sometimes they inject the THC or the CB1 agonist. Sometimes it's oral. Sometimes it's inhaled. And doses used in animal studies vary dramatically, everywhere from 1 milligram per kilogram in terms of THC to 30 plus milligrams per kilogram. And this is a study over here just kind of looking at how different doses in animals are associated with different levels of THC. So here you see 0.3 milligrams per kilogram, very much on the low end of what's in the blood, and 3 milligrams per kilogram, a little over 50 nanograms per mil. And then the 10 milligrams per kilogram, we see about what we see in humans. So when we do a study in humans, especially if it's inhalation, and I'll show you these data in one of the upcoming lectures, we see a number kind of close to this number over here. But very rarely do we see these kinds of numbers. Okay. Also, it's very important to think about what does a quote change unquote in the brain mean, right? Many of the studies that report associations between cannabis use and brain morphology or function they do not include data that would help interpret the association. So, for example, if a study finds a difference in the shape of the amygdala, how does that translate either positively or negatively in terms of behavior or cognition on a day-to-day basis? And nobody knows the answer. Also, causation or temporal precedence is not possible with human studies. Note that we cannot randomly assign people to use THC for 10 years to find out if THC actually causes changes in the brain, right? There's no way to assign people to conditions. So we can't prove causation. It's always possible that differences in the brain precede cannabis use, and we've talked about that a little bit before. So in other words, there may be shared vulnerability factors that underlie both differences in the brain and differences in cannabis use. Now, this is important. NIDA is doing a huge study called ABCD, in which they're recruiting 10-year-olds, 10,000 10-year-olds, so they will be able to establish temporal precedence and be able to look at, do changes in the brain precede cannabis use, or does cannabis use precede changes in the brain? So we will have some more definitive answers about these questions, 5 or so years down the road. Okay, so here's an example. Example number 1. This study just came out as I was teaching my spring section on cannabis and health. This is a great group of people who did this study, published in a great journal. And the upshot of the study is that one joint produces change in gray matter. So these are adolescents. They found adolescents who had used cannabis just once or twice and looked at them specifically. And the bottom line is the study suggests that just one or two times of cannabis use can change the morphology of the brain. Here's another example, completely different. This is looking at the effects of THC in mice. And what this study suggests is that age-related cognitive impairments in mice can be reversed by an extremely low dose of THC. We're talking super low dose of THC here, way less than a milligram, right? So, or less than a milligram. Again, a very low dose of THC if you do the translation between mice and humans. Okay, so what is my point here? My point is, in both cases, I think it's important to have healthy skepticism, right, about what exactly is happening in these studies. It's important to evaluate the study linking one joint to changes in brain volumes very carefully, because it's a bit much to believe that using just once or twice will cause significant change in brain morphology, especially given the data I showed you previously. Also, it's equally difficult to believe that microdoses of THC reverse age-related cognitive decline, right? So I have here this question: which one do you think is more credible and why? And hopefully you're going to adopt some healthy skepticism here in both cases, because what we want to see is that these things are replicated in order to believe them. So healthy skepticism, I think, is very important in the cannabis world in general, and also always thinking about how your own confirmation bias may bias your evaluation of a given study. And my heuristic is, if it sounds too good to be true, probably it needs to be replicated. So, okay, conclusions. I want to circle back now to the brain here. Lots of studies suggest an association between acute and chronic cannabis use and measures of brain function and structure. So I told you before, probably there's not much there in terms of cannabis use and morphological changes, but I think it's the evidence suggesting that cannabis use downregulates or reduces CB1 receptors in the brain, that I think is pretty solid. Also, it makes sense that some of these studies suggesting that cannabis use might be associated with changes in affect or emotion regulation. Also, that makes sense. And then finally, the suggestion that changes dopamine signaling and reward, I think that's also on fairly solid ground. So there's definitely some evidence to suggest that cannabis use is associated with functional changes, even if there isn't for structural changes in the brain. And it makes some common sense, right? Again, cannabis is not harmless in general, regardless of what it does to your brain. There are pretty clear effects on cognition and learning, also on mood, and it makes sense that would be translated in some way in terms of differences, functional differences in the brain. One important point when we're talking about risks of cannabis, that risk profile probably varies dramatically between young people and old people. So when we talk about these changes in the brain, other than the mouse study looking at old, elderly mice, we're most often talking about young people with respect to changes in the brain and changes in cognition. So very important to keep that in mind.